Recording. Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. Yesterday we took the bold step of deciding to actually initialize the hardware, 3D hardware acceleration, because I kind of got tired of not having any VSync in our game, and I don't really know of a way on Windows anymore to actually get somewhat reliable VSync without going through one of the 3D APIs. In the old days, there was like a direct draw API that you could use to get VSync separately from, separately from the 3D driver. Now it's not so easy to do that. That's kind of all very legacy stuff, and I don't know if you can really count on any of it anymore. So we initialize that, and today we have to do some work. We may have to put the work off, because let me tell you what happened. I found the HDMI capture card. Here it is. This is the one we bought for Handmade Hero. And I've been meaning to switch to it so that we could we could have a separate machine that streams so that we wouldn't take up any system resources with OBS and have a cleaner way to look at profiles and stuff, right? But when I went to plug it into this machine, I discovered that this machine's graphics card is so old, it does not have an HDMI output. It's got DVI and DisplayPort. So I need to get an adapter. But as soon as I get an adapter, or a different graphics card, I guess, once I do that, then we will be able to do it. So maybe I'll try to, I might have one at the office. I don't really know. I'll look tomorrow, or I can order one. But it means that that's a little bit of a problem, and I don't really know any way around it. Now, it's possible that OBS, for all I know, might have some way of me being able to do some kind of a game capture thing here that would allow you to see it, but I just don't know. So, unfortunately, we may be a little bit blind, because as you know, when I run the game, if you were here yesterday, you know that what happens when I run the game now is when we start drawing an OpenGL, I can see it and you can't. We made a thing that just draws a pink screen. I am seeing the pink screen. You are not seeing the pink screen right now, apparently. We're going to go ahead and just do what we would need to do anyway, and I have a bunch of white Blackboard stuff to talk about today anyway, so that'll take up some time. But hopefully we'll be able to get the capture card working, and then we can just go with that from now on. If not, we'll just start fussing with OBS to try and make it so it both captures the game OpenGL and the desktop. Either one of those two separately works okay. I just don't know if there's a good way to make it so that you can fluidly switch between them, unfortunately. So that's the part that I don't actually know. So let's go ahead and do a brief recap of where we're at, and then I'm going to go to the Blackboard and kind of give you the overview of how 3D hardware works, because nothing I do with it will make any sense if you don't have a solid grounding of how that's actually supposed to work. So, okay. If you remember from yesterday, here is Win32 Handmade, and we basically just went ahead and did a initialize OpenGL, Win32 initialize OpenGL, and there it is. And you remember the stuff we had to do is we had to set up what we wanted sort of our drawing format to be. We had to tell Windows GDI that was what we wanted our window to be set up as. We then had to create an OpenGL context, which is basically something that sits on top of a Windows device context that allows us to access OpenGL through. Then we set that up as the current one for our thread, and then we were done. And so then the only other thing we had to do is actually use that code somewhere. And so we had just this very simple thing which set a drawing region, it set what color we wanted to clear to, and then cleared the color buffer to that color. We then called swap buffers to present the drawing that we had, and that was it, right? That's the end of it. So hopefully that was all pretty understandable, and now we need to take the step into actually calling the 3D graphics hardware in some way that does things we actually want. Because clearing the screen to pink is nice and all, but it doesn't really help us get our game on the screen, right? Okay, so let's go ahead. Let's see what day. Today is day 236. There we go. Let's talk about GPUs. All right, so what is a GPU? You all basically know what they are. If you've ever played a game before, or you're a gamer in any way, obviously you know about them, even if you've never done any programming. You know about them. And we talked a little bit about them yesterday, about how they sort of came out of the old concept that there was a graphics workstation, which is basically a computer that had dedicated hardware in it that was designed to do graphics operations. And eventually those things became daughter cards to put into PCs, with companies like 3DFX and Nvidia sort of bringing that to fruition. And now that is just a standard expected thing to have in a PC, to the point where they now are basically the same as those workstations back then. They're much more powerful than the workstations, but they're basically the same conceptually, in that now it's basically not even possible to really buy a PC that doesn't have a dedicated 3D hardware acceleration part on it. Even if you don't buy a big beefy desktop style one, then your CPU now oftentimes has a 3D accelerator built into it, right? Like Intel oftentimes now ships, the CPU is 30% of the die, and the GPU is 70% of the die. So a huge portion of your actual physical chip that you buy from Intel is actually just a GPU on there. So in pretty much all respects now, anything that you buy, even a cell phone these days, oftentimes looks a lot more conceptually like an old silicon graphics workstation, in that sense that there is dedicated hardware for 3D graphics built in, and it's expected. So that's the world we live in now. But we did not grow up that way. We did not start out in that, with that basic design. And so it's really kind of uncomfortable the way that the system is architected for CPUs and GPUs. It's kind of a very legacy, very clunky way that these two things work. And so let me give you a little bit of a background on how that works. So you know very much about the CPU now if you've been watching Handmade Hero. We know that basically there is, main memory, right? It's a big old chunk of memory. This is oftentimes something like 16 gigabytes today, right? And then you've got a CPU. This is like a Core i7 or something over here. And there's a little bus, right, that allows the chip to access this memory and to put things, send things and get things back from this main memory, right? Everything's grand. And then there's some like I/O ports, or who knows what else is happening on here. And maybe some other people are viewing this memory, like, maybe the USB controller can look at it. Who knows if it can? Maybe it talks directly to the CPU. I don't know. Doesn't matter. We don't care about any of those things. The only part we care about is this part right here, which is to say that this is what we've been working with almost entirely so far. And with this particular system, the way that it is right now, with this diagram, there'd never be any way to get something on the screen, right? The screen's over here. Here it is, right? And somehow Handmade Hero's been showing up on there, but we don't even really know how. And the reason that we don't know how, even though this is like, we've been doing things as low level as we possibly can on a PC, the reason that we don't know how is because at some point, the memory that we're trying to display actually can't live in this main memory anymore on this particular machine. And the reason for that is because the actual memory where the display actually lives is over on the GPU. So here's the GPU, and here's its memory, right, on the card. This is actually physically on the GPU card, right? And this is something, oftentimes like 1 gigabyte. It's smaller. It's almost always smaller than this, right? Now, what has to happen, and the reason this has to occur, is because the physical plug, like literally the cable, the HDMI cable, or in our case, the DVI cable, is connected to this memory, right? Like, this is the card, this is the thing in the computer that has the plug on it that connects to the screen. So if you're going to show something on the screen, that something has to be in this memory. So what happens is, at some point, Windows, right, Microsoft Windows, running on this CPU, when we have asked it to, has been moving our bitmap, right, this bitmap that we drew, has been moving it silently for us over to the memory here, and then this GPU, the card, has been transferring it over the HDMI cable to the screen where it is displayed. And there's actually hardware in here that's designed to read out of memory like this and encode it into an HDMI signal and put it out the thing. Like, that's actually part of the GPU's chipset, right? There's a little chip in here that'll do that or something. It used to be called a DAC, right? A digital analog converter, because the signal that was going out was analog, but I don't think they really call it that anymore. I don't know, maybe they do because it's still sort of an analog thing, but since HDMI is digital, it's not, the word DAC is a little ambiguous there. But I don't know, I'm not a hardware guy, I don't know the terminology they use for those sorts of things, but that's what's happening. Okay, so what we've been doing so far is we've basically just been asking Windows, hey, look, here is our bitmap that we made ourselves. We have it in a particular location in memory, and you remember where this was happening. This was happening where we were calling stretch DI bits or anything like that. So right here, yeah, Win32 display buffer in window. This call right here, or this call right here, depending on which branch we were in, that's what did that. We gave it the address of where this was, we told it how big it was, and then it moved it over to the GPU, and the GPU displayed it. That's what was actually happening, okay? Now, on some computers, that doesn't have to happen. If we were in a situation instead where we had a CPU-GPU combo, right? So let's say this is a Skylake part, right? So the latest Intel chip, it's got one of these on it. They have a shared memory architecture, potentially, which means that that picture that we drew with the CPU is actually in the same memory as could get scanned out, right, by that HDMI cable. Essentially, the HDMI cable, or the DVI-X cable in our case, is actually plugged in to the unit on the computer that has the main memory. And so it's not always the case that this transfer has to happen. It's only the case if the GPU is on a separate card, and in this machine it is. So this is like a typical desktop setup, but a typical mobile setup, right, might look more like this, where there's just one shared bank of memory. Okay. So let's talk about what this means for how things have to happen. All right, because this is the diagram that concerns us. And the reason that this is the diagram that concerns us instead of this one is because on the PC, you are often on a high-end gaming machine looking at this. So when you're talking about optimizing, you're usually talking about optimizing for this, because this is the thing where the, you know, bro's got 2 GeForce Titans in there or whatever. So there's actually more, there's more than one of these, right? So this is the thing you're looking at for the really high-end optimizations, right? This is the thing you're looking at the lower end. But because this is the worst case, meaning this is the most disconnected things can be, and it's an important case, this is the one that everything's designed around for the most part. This is the worst case is this, where we have 2 different sets of memory. And so even though there are plenty of machines out there that just have one unified memory bank for everything, we have to deal with this diagram. So even when you program this guy, you're still effectively programming it as if it looked like this. And the reason is because you're trying to ship one game that runs on several different types of GPU, right? And so if you pretended everything was always in main memory, it would come to a screeching halt when it tried to run on one of these. So this is the diagram that concerns us, which means what we're looking at here is something that essentially looks like this. So here's the CPU, and here's system, we'll call this system RAM. Here's what we'll call, graphics RAM, and here's the GPU. And these 2 things are connected by the PCI bus, right? That's that slot that you plug things into, right? Where you plug the graphics card into. So the GPU has fast access to everything in here. The CPU has fast access to everything in here. But everything that's not, right? So if the GPU wanted something from system RAM or the CPU wants something from graphics RAM, it's got to go over the PCI bus. Maybe. Again, if it's a Skylake chip, if it's an Intel integrated graphics part, something like that, it does not because it's all system RAM. But assuming that we're talking about something that's like, oh, this is an Nvidia part and this is an Intel part, well, then there's this bus. And so there's a speed hit that you take transferring these 2. And oftentimes the speed hit isn't so much about bandwidth in that way that memory bandwidth is often very good. It's rarely about how fast you can transfer things. It's more about the latency. It's more about how long it takes from the time you start to the time you finish, right? It's kind of like a very, very big pipe, right? That's very long. So it's, once you know you're going to send something, you can send a lot of stuff down it, and it all gets there to the end quite nicely, right? But the distance it's got to traverse is quite long, so from the time you start sending it, you got to wait a while till you get it there. right? And that's pretty important. There's a lot of latency in this part, right? So you got a lot of bandwidth, you can send a lot of stuff down, but it takes a while from when you decide you're going to send it. It's not like normal memory. It's quite a bit more. So anyway, this is the diagram that we're concerned about, and let's just talk briefly so that you kind of understand. In fact, I don't know, maybe today might be a good day to just get all of this out in the open so you kind of have a good feel for it, since we don't have the capture card anyway. Maybe we'll just do all Blackboard. Who knows? I'll go in as much detail as I think is warranted as we kind of go through here. All right. So what is the what are these things? Why do we even have them, right? I said I use terms to explain sort of where it comes from, and implicit in those terms are a whole bunch of decisions and reasons that we haven't really stated explicitly. So for example, why do we need this GPU? Like why can't this CPU just do the things that we need it to do? Like what is the idea behind it? Like what's going on here, right? And so the reason is because these two devices are designed for very different purposes, and they make different trade-offs, both in terms of their memory architectures and in terms of their instruction set architectures. So they are getting closer together, but they started out very far apart. So I want to sort of draw a little bit of a faux diagram here. I don't mean for this to be highly technical, but I want to say something like this is a CPU in 1999, and this is a GPU in 1999. Okay, so just before the turn of the millennium. And I would say that right here, this might be we'll call it the PU, the processing unit of 2030, let's say. I don't know, maybe, who knows. Essentially what has happened over the years is CPUs and GPUs kind of move towards each other, if that makes sense. So they started out very different, and they're becoming very similar. So part of the understanding of why we have two different types of chips is not as readily apparent if you look at what the chips look like today, but it's much easier to understand if you look at what they looked like a long time ago. So a long time ago, what was a CPU? Well, a CPU was something that was mostly operating, right? Single instruction, single data, you might say, right? Remember we've talked about SIMD, right? Which is like single instruction, multiple data, those big wide vectors. It was mostly something that looked more like this, where it was like saying, oh, I have stuff like, a move instruction. I have to move like one 32-bit value, out to some memory somewhere. I'm going to pull another one in. I'm going to look at its contents. I'm going to do a branch, right? So they tended to be things that were built for serial execution, right? So fast, single thread, single line execution. So basically, CPUs, what they tended to look like is I'm trying to do a series of operations as fast as I can. Those operations operate on one thing at a time, and they're very varied. It's a very random, heterogeneous, right, instruction stream. There's no rhyme or reason to it. It's just whatever, okay? Meanwhile, a GPU is an incredibly, incredibly specific thing. And what that is trying to do is it's trying to take blocks, and it's trying to fill them in with pixels. So it's just trying to figure out what on screen is supposed to fill with pixels, and I'm trying to fill them with predictable, linearly, or sometimes perspectively interpolated color values, right? So most of what I need to do is I know I've got basically these things called textures, which are like images. I'm pulling from very regular, very predictable parts of them, right? Like I'm pulling from specific coordinates to kind of map them into here, and I'm filling them out, sort of stretching them a little bit, just like we wrote, exactly like the kind of code we wrote, but even a little more primitive than that, if that makes sense. And it's very predictable. This texture stuff, this is read-only. You never write to it. This is basically write-only for the most part, but it does have blending, right? It's got the ability to like kind of blend on top. But for the most part, you never even really read from this thing, right? And that's sort of where things were, I don't know the exact dates here, but, pre-millennium, okay? And so this thing had a very specific memory usage. It did very few writes to the texture area, and almost exclusively tons and tons of writes to this stuff. It always kind of read, because of bilinear filtering, it always read in like little quadrants. It knew that it would tend to read little sections out of this, right? It would rarely read like a whole row of a texture. It much more often reads like a little chunk of a texture for whatever part was on the screen. It knows when it's filling like generally these little regions about, the size of what a triangle should roughly be on the screen, and so on and so forth, right? Very, very regular. These things looked very different back then. As they started to become more general purpose here, and as CPUs started running into like barriers of how fast they could run single pieces of code, these two have moved much closer together. So over the years, when we got to say where we are right now, where it's like it's 2016. And here's GPU 2016 and CPU 2016. These things look remarkably, remarkably similar, right? The CPU has either an 8 or a 16 wide, right, SIMD unit. We talked about this. GPUs actually look a lot like this. They have either a 16 or 32 wide SIMD unit usually. And there's been, now there's so much stuff that happens with shaders. And we added shaders, which are basically programs the GPU can execute. We added unordered access views, compute shaders that can write to anywhere in memory, can read from anywhere in memory. Basically what happened is a huge amount of general purpose stuff crept into these, and a huge amount of like perf specific stuff crept into these. And so you started seeing them converge to something which both could do both, right? Both a CPU and a GPU are now sort of set up to do both things, and there's just some, because of their legacy, that they do worse than others on either side, okay? And so a lot about this architecture. We've talked a lot about this. And so what I'd like to do is kind of give you a perspective of like sort of what this architecture sort of looks like at a very high level, because we don't even really know. Like, Nvidia won't tell us exactly how their chip works internally, right? So we don't necessarily know, but we can give sort of some examples of sort of how it works. All right, so now instead of a device that's purpose-built for just doing this, like filling triangles in exactly this way and reading from texture memory and doing a very specific set of operations on them, all that's out the window, because now we've got shaders on our access, all these things. So now what a GPU actually looks like is usually just a ton of ALUs, right? These are the arithmetic logic units. These are the things that do, like, remember when we did our renderer? These are the things that do like the 4-wide multiply. Remember when we did these things that are like mul, ps, right? Those instructions, and they take two components, like an A and a B, and it's like, it multiplies A0 times B0, A1 times B1, A2 times B2, A3 times B3, right? You know that? Well, that is basically what a GPU is. A GPU is a giant one of these. So instead of a 4-wide one, or an 8-wide one, which like the Intel desktop chips now have 8-wide for these, they are more like 32-wide. So they're more like saying, hey, you know what? Or I guess like 16-wide, like I said, is another one. I think Nvidia is 16-wide and AMD is 32-wide. I don't really know. I have no idea. Nobody tells me these things. I don't even know. It might be secret, for all I know. Anyway, they're basically these giant 16-wide or 32-wide ALUs. So they basically take in, some giant number of floating point values, right? Something that looks like this, with literally that many floating point values in it, and they do some arithmetic ops on them. Typically one might be a MAD, like a multiply add, so it'll take like an A and a B and a C and do A times B plus C, right? It might have that kind of thing, so a big old arithmetic operation it could do in there, and they're just set up to do tons of these. And what you see, so I don't know if you guys ever looked at this, maybe you wondered what this was, but if you do like list of Nvidia GPUs or something like this, or you look at how they quote their numbers, you'll see stuff like core count or something. they'll list on there, right? So we come in here and it'll say something like, let's see, processing power, bandwidth, transistors. I don't know where that is. Where is it? Do they have those? Let me see. See if they list these on. If not, we can just go to Nvidia. It's like, let's see, Nvidia Titan number of cores. Okay. So this is what they say, right? They say CUDA Cores 2880, right? Now, you think about that and you're like, well, how many cores does my CPU have? And you're like, oh, maybe it's got 4 cores. And you go, oh, well, how many CUDA cores does this GeForce have? It's like 2,880. It's like, oh my God, it must be so much more powerful than the CPU. Well, as you'd expect in anything with marketing, this number is completely ridiculous, right? What is a CUDA core? Well, a CUDA core is actually the number of GPU cores, right, times the width, of the ALU times the number of ALUs on that core, right? And again, you know, I don't know a lot of the specifics of these things, so I'm just giving you a basic ballpark here. But if the ALU is 16 wide, right, then this number is 16. And if it has, say, 4 ALUs on it, then this number is 4, right? So the actual number of cores when they list something like this is actually quite a bit lower than what they're actually saying. It's as if Intel multiplied the number of cores by 8 because they could do 8 wide instructions. And if they have 2 ALU units that can each do one of those, right, on each core, then they would multiply it by 2 again. So it'd be like 16 times or something, right? The actual number that of cores that's actually on there. Yeah. So it'd be something more like saying, oh, you know, take this number and divide it by something big. And I can't, they might even do a little bit more than that. Like it might even be, like if they could, how many they could issue. I'm not sure. It's something ridiculous, but point being, this number is has nothing to do with what you might think an actual core was, if that makes sense. I wonder if we can find somewhere, if someone out there knows definitively how NVIDIA computes their core count, feel free to post it on the stream, because it's an equation like this where the actual number of cores actually works out to be something fairly small. I don't know, let me see here. So 2880 divided by 64 is 45, right? So yeah, in this equation, let's say we did this, right? Then the actual number of cores in this thing is 45, right? So yeah, it's a lot of cores potentially, but it's a lot less than 2880 sounds like, right? So just something to be aware of. Anyway, so what these things are, again, is they're cores just like a normal CPU core, as you would expect, and there's a lot less of them than you think there are when they write the thing down, but they're simplified, so they don't have nearly as complicated as an instruction set as an Intel CPU. They don't necessarily have the same kind of caching or those sorts of things because they're set up for different, for sort of more streaming operation, but they're basically the exact same thing. So they have like all the instructions you expect to see, like a mul and a div and an add and whatever. They have all those things, although sometimes they're all done with the same thing. So sometimes you may have something like a multiply add. Well, if you have a multiply add instruction, you don't need a multiply instruction or an add instruction. You can just do a mad with 0 in one of those places and you end up with whatever you want, or a mad with 1 in one of those places and you add whatever you want, right? Okay. So that's what a GPU core actually is, and the way that the GPU core works is a lot like what we saw when we did our rasterizer. Remember how we did it? We said, oh, we can do 4 pixels at a time, right? So what we did is we said, let's do A, B, C, and D pixels at the same time, and that way we can fully utilize that system that Intel has for doing 4 wide multiplies, right? Well, a GPU does exactly the same thing. It just does it wider. Now, you might ask, why doesn't it, does it do 16 in a row? No, and the reason for that is that most triangles are fairly small, right? The higher the higher definition the game, the more detailed the models, the smaller the triangles get. Triangles don't usually fill that much of the screen, right? they tend to be kind of tiny. And so when you're doing pixel fill operations, you kind of want them to be more square, right? You want them to be shaped more like, like this, and less like something like that, because the triangles don't tend to look like that. They tend to look more like that, right? So what they do instead is they just add a vertical component to it. Instead of just doing 4 across like we were doing, they do 4 across, 4 down. So they do 16, they do them this way, so they basically take, pixels. They take pixels that look like a pattern like this, and they just unpack them, right? Well, they don't, there's really no unpacking per se, but I mean, they just kind of like think of them this way, right? So then they do these giant operations on those, and off you go, okay? And they do exactly the same sort of stuff we did. The triangle probably only touches some of these pixels. They mask, just like we did. We had our mask where we were like writing, and we didn't want to write the final one, so we masked it out. Same thing. It's all exactly the same. So the way we wrote our rasterizer is very, very similar to what these things are doing internally, right? Okay. So these GPU cores, it's got a bunch of those cores, and they're designed to just basically take shader code, right? That shader code that you write when you see like a DirectX shader or whatever, that kind of thing. Shader code, which is very much like CPU code now, and they're designed to execute that 16 or 32 wide. That's what they're trying to do. I don't know if any are 64 wide. I don't know how wide they get, but that's what they're trying to do. And so that's why a shader is not quite the same as CPU code. And the reason is because you have to remember an Intel chip is highly optimized for executing basically straight line CPU code that's got a lot of branches in it, right? It's got jumps, branches, it's got random memory access, all these things. Well, GPUs aren't set up to work with that, right? They're not made to do this. They're made to do much more coherent code. And so one of the reasons you can't just take CPU code and shove it into a GPU and expect it to get faster is because the degree to which a GPU can be faster than a CPU is entirely dependent on parallelism. And it's dependent on 2 kinds of parallelism. One, utilizing the fact that there are more cores on a GPU than a CPU. Maybe there's 10 times more cores. And utilizing the fact that the ALU is much bigger. Maybe it's twice as big, maybe it's 4 times as big, maybe it's 3 times as big, something, but it's got a boost there. What that means is you have to be able to go 16 wide. You have to be able to go 10-way parallel. You have to be able to do those things with this code. If the code can't do that, it's inherently not going to get any faster on GPU. In fact, it probably will get slower because GPUs tend to run at slower clock rates with worse support for arbitrary stuff. Okay, so with that masking part in mind, remember I talked about the masking here. With that masking part in mind, let's talk about how those ifs work, right? So in a CPU, you've seen how this works. We say if x, do this, right? Maybe let me do something here. Y equals 5. If x, y plus equals 7. Okay? So in a CPU, what we expect to see here is something like taking the location of y. So here's the place that we're storing y. We take the 5 in this instruction and we put it in there. We then load in x, so whatever's in x, maybe in x is a 1. We load that in. We do a test instruction on it, right, to see what if it's equal. We do some kind of comparison of some kind. And then we do a jump. And we do a jump based on the result of the comparison. So either we skip, the jump doesn't happen, and we do this piece of code, or the jump does happen and we skip over it. If we do get to this piece of code, we're then going to take 7 and we're going to write it back into here, right? We do an add instruction, and we overwrite the 5 with 5 plus 7, which is 12, right? Or we don't. So we're used to thinking of code in this terms, where we go ahead and say, oh, okay, do a test, jump over. So we think of it as doing like either or, and maybe there's an else clause here, right? So we think of code in terms of either or, right? If this, do this, otherwise do that. That is not how anything works in the world of wide instructions. The reason for that is if this is 16 wide, well, what does it mean to do an if? We've got 16 different things here. Some of them will be yes, some of them will be no. What that means is that in the wide world, in the GPU world, all branches are always taken, basically, right? So what happens is, when you get to an if statement in shader code, what that actually compiles to is not an if statement at all. It compiles to both branches, but with a mask. So it first does a test here to see which slots of the 16 wide lane are going to do which branch, right? And it produces a mask that's like, oh, these are the places that need to do this branch. Then it computes fully the result of this branch, computes fully the result of this branch, and then uses this mask to AND them together, and an OR, mask and OR them together, to produce the correct composite result. So to the extent at which this if ever actually happens with a jump is only if all of them have the same value. Basically, ifs with a jump are now just an optimization in GPU land. They're a thing that if you happen to have all the same value and know you can skip one whole side of the branch, maybe it will. Maybe the GPU is smart enough to do that. Maybe it's not. But that's all the jump is now. The jump's an optimization, but it's not the actual control flow. The control flow actually always goes through both branches, conceptually speaking, and the only time that it won't is if all the values happen to lie in one side or the other of the branch. Okay? So when you think about how GPUs execute, you have to kind of change your mental model a little bit into more of the code is all straight line. There's no such thing as a branch not taken unless you're optimizing a particular case. They're all taken. How does this work with loops? You've seen loops, right? Same thing. Loops, they loop until the very last guy no longer tests for the loop. So even if everybody else, all the other lanes had finished and they only need to do like 5 loops to this thing, but this last guy at the end, he's got to do like 100 iterations because that's just what his lane was set up to do, right? You do 100 iterations on everybody, and every time through the loop, you just throw away 15 of your 16 calcs, and you are sad, right? Now again, that's the basics of GPU. I'm sure GPU vendors do all sorts of things to try to improve performance here, like maybe they notice when you end up with a 4-4 split and try to merge in some other work from somewhere else. I have no idea how sophisticated they try to get with some of these things, but that's the basic idea. And that is why you'll often see things like, they'll talk about a warp. There'll be things that refer to like everyone in the warp or something. Well, that's what a warp is. A warp is 16 or 32 guys who are in it together. And they're going to take all the branches and all the loops together until all of them agree. And so the only time when they actually do any branching or any terminating of loops is when they all agree. Otherwise, they're all going through everything, every time, always, right? And you can see why that's important to understand from a performance perspective, because if you write your code in a shader thinking that it works the other way, you're going to make very, very different decisions potentially than if you know that this is the basic way that it works, right? Okay, so that's the basics of how the GPU execution works. The part that I don't know very much about, because I've never seen any declassified stuff about how this works, is that's a part of the GPU that's all those ALUs. That's like, we have 48 ALUs on here or whatever. What I don't know very much is how the bookkeeping part of the GPU works. Because obviously there's all this dispatch that has to happen here, like, hey, go do the transforms on this vertex buffer. Hey, go fill these pixels. Hey, do whatever, right? That part I don't know very much about, and I don't know how much you can even know about it if you don't have some kind of NDA declassified information. But this is how those cores work. And this now, because like I said, GPUs have gotten so general, this is actually just true. It's really just this, no matter what you're doing. If you're filling pixels, it looks like this. If you are transforming vertices, it looks like this. If you're executing a tessellation shader, it looks like this. It all looks like this now because shaders have gotten so, the ability to do so much general purpose stuff that they really can't design CPUs to take advantage of any specific thing anymore like they used to. We're not here, we're here. So it's really just big old ALUs that can basically do anything, running fairly generic code, right? At a relatively low clock rate compared to your CPU, but very wide. And with a lot of those ALUs, right? So a lot of floating point operations that it can do. All right. So that's what a GPU is. That's really what it is. And there's some still special purpose hardware in there. For example, there's usually a memory unit that's very good at fetching textures. So there's like a thing that can go fetch and do like a DXTC. You know, there might be like a DXTC texture compression, a thing that, like a hardware to get textures really fast. There's usually a texture cache that sits somewhere in here that's like faster than the graphics RAM. So there's a bunch of complexity that comes in here to try and make the GPU fast. But at the end of the day, it's just something that's executing code very much like what we see on the CPU side, only instead of having a lot of like branchiness, iffiness to it, it's text to be very wide, very masky kinds of stuff. All right. So where does that leave us? We're going to get into some of that. So I want you to kind of be aware of that and have that understanding. We'll revisit it later because when we actually do our GPU code for drawing Handmade Hero, I'll be re-mentioning some of that stuff. So keep that in mind. But right now, what we have to do is look one step removed from that, basically. We have to worry about how we're actually going to get the GPU to start doing the work that we want. That's the work that it's actually going to do for us, right? It's got all these ALUs. It's going to do all this stuff for us, right? But we have to figure out how to actually get that happening. Okay, so this is the diagram that concerns us. What tends to happen, the way these things usually work, is there's a concept that memory is mapped. And what that means is typically some portion of the system RAM will be mapped such that it lines up with a portion of the graphics RAM. And so what will happen is the CPU will say, I would like to put some stuff in here. So it will write into memory that is mapped. And that memory will then get transferred over the PCI bus to essentially, fill in what it needs, right? That's the concept of mapped memory. And that's just like when two devices want to have some shared memory to each other, they can map it so it's mapped in one space, mapped in another space. Now, as you might imagine, that could go both ways. So the GPU could write things in here, and then I'd see it over here. And again, that just gets transferred to the PCI bus. When there are changes here, they show up here. When there are changes here, they show up here. And that's a coherent, like, mapped memory thing. And you can, that's a thing that exists. But nowadays, as you can imagine, the graphics workloads are so heavy that you typically need to be a little more aggressive with things like the way that works. So what happens now is oftentimes GPUs have essentially DMA transfer controllers. That they call like copy engines, oftentimes, which are parts of the chip that literally do nothing but sit there and take instruction from you about where to grab stuff. And they're just sitting there grabbing things and moving it into their memory, right? And I don't know, but I don't think they actually require much in the way of mapping other than just it has to be in a part of memory that the DMA controller can see. And so the mapped concept, if you're actually talking about what happens at a lower level, oftentimes doesn't end up meaning that we're actually trying to mirror memory between these two things. What mapped ends up meaning most of the time when you're using a GPU nowadays is just that you put something somewhere in a range of memory that the GPU's bus controller, copy engines, can see and get, right? Because in general, I don't know the specifics of the PCI bus. I was an Amiga guy, so I don't know PC bus sorts of stuff at all. But basically, my understanding is the PCI bus, devices have to have mapped regions that they're allowed to read, and I don't know to what extent they're actually allowed to read any given memory. But even if they were allowed to read any memory in the system, you have to remember that the CPU has virtual memory, right? We talked all about this. So, your application sees some virtual memory space. You don't even know if that memory is all stored in actual memory right now. Some of it might be paged out to disk, whatever. So this guy, the actual GPU, when he comes over to get memory, it had better be in physical memory at the very least, right? Because if it's off on the disk, forget it. He doesn't know anything about the disk. He doesn't know how to access the hard drive, right? That requires CPU intervention. And so what actually needs to happen here, more importantly than anything else, is this concept that we need to map the memory or whatever. We need to lock it down. is one way to think about it. We need to pick a range of physical memory and actually say we're going to leave this in here and we're not going to let it leave or get transferred out or swapped or deallocated or anything else until this guy finishes getting it and we receive confirmation from him that he no longer needs it, right? And so again, so this concept of mapping memory or thinking about memory that both the CPU and the GPU can read tends to end up being a lot less about thinking of it in terms of shared memory with like synchronization between it, and more about transfers where we lock a piece of memory on the system RAM side and then we tell the graphics chip either put some stuff in there please or move some stuff out of there please into your memory. Okay, and so you can kind of see where I'm going with this. That is exactly what we need to do if we are going to actually send our image, our bitmap, down to the graphics card. So we're going to need a way to do that, right? But before we can do that, even before we can do that, we need something else, which is we need the way to tell the GPU to do anything at all, right? Because we could lock down a piece of memory and put some stuff in it, but how are we ever going to tell the GPU, hey, come get it? The GPU needs some way of knowing what we're even trying to tell it to do. Okay. And so what's that? That's a thing called a push buffer. Now you'll notice we have a push buffer, and it's the thing that tells our renderer what to do. Well, guess what? That's modeled exactly after how the GPU works. So what basically happens is you start off by taking some chunk of your system RAM, you lock it down, and into there you're put actual commands, which are like, I shouldn't say commands, but basically like a known binary structured thing, just like our push buffer that's got like stuff on it, like do this, do that, do whatever, that has pointers to other lockdown pieces of memory, and the graphics card is instructed to read from the top of that and do what it says, right? So it grabs that push buffer over here into its memory, presumably, starts executing off of it, does the things in it, and in there are things like, hey, go grab this other chunk of memory, bring it in here, draw these triangles, do whatever, load this shader, set this state, blah, blah, blah. So the model of execution you have to think of in terms of what's actually going on in the system is, well, it looks kind of like this. Here is us. Here's Handmade Hero. Right? And we've got an old CPU, and the CPU is executing in Handmade Hero, and that's all great. At the top of our address range, right, the OpenGL 32.dll code, the system drivers and stuff, they got mapped in. And so once in a while in Handmade Hero, we got to do some stuff with the graphics. We're going to call out to something out here. These are functions, again, right, that are mapped into our address space when we loaded in that DLL. We're going to call some of these, and what they're going to do is they're going to prepare, in some of our memory, right, they're going to prepare some of this push buffer data, right, or something like that. Right? They're going to prepare, we don't know, we can't even see because this is, again, Nvidia's code, whatever. They're going to prepare some of that push buffer data in our memory. This is our memory, by the way. This is our thing, right? Handmade Hero, right? This is our code. And here's our push buffer. Here's some more code from the operating system, whatever. This is our main memory. So the CPU is going to do that. The CPU will prepare this push buffer, right? And then at some point, and this is entirely up to the driver and how it chooses to do synchronization, whatever, at some point it's going to take, and I assume this has to happen, it's going to take what's called a ring transition. Now you don't really need to know very much about what that is, but point being, CPUs have the concept of rings. There's like typically ring 2, ring 1, ring 0, ring -1. Yes, that's a real thing. And what these are, they're basically privilege levels for what you can execute. We are just an application. We have essentially no privileges. We can't do most of the things that the kernel can do of the operating system. We don't even know what the memory map is. Like, we see a virtual address space, right? So we don't even know where the actual physical memory is. We got no idea what's going on, right? But the kernel knows all that stuff, and it can do all that stuff. And part of the reason for this separation is obviously for security and for stability. You don't want like one errant application to crash your whole machine if you can avoid it. So basically these rings of privileges, obviously on the CPU, I think we've talked on them before, help to ensure that happens. So at some point after we've built up something and we need it to actually go off, we'll actually take a transition into the actual driver code, which is actually in ring 0, right? So we happen on some other ring, right, that's higher than ring 0, that doesn't have those kind of privileges. Then we go to the actual ring that can actually talk to the hardware. And in here, there's like something that is going to kick off our push buffer, right? So this push buffer might have had, like our memory, it may have mapped it to a physical thing. This is our virtual address space, right? It may have already been locked to physical, in which case the kickoff can kick it off directly, transfer and kick it off directly. It may not have been, in which case what it will do is actually do a copy first. And I have no idea whether that happens in our ring or in their ring. I have no idea, right? But at some point inside the ring 0, at least I assume you still have to be ring 0 to do this. Maybe they've changed that. Who even knows? But at some point, it will do what's called a kickoff, which is basically saying this push buffer, with all the stuff that you told the graphics card to do, now is ready to go. So start executing it on the graphics card. And that will trigger this transfer, and the GPU will get that and start working on it, right? So the mental model that you should have looks a lot like this. It should be, I've got stuff in my memory space that I'm building up with calls to OpenGL. And we can't build it up manually. The reason we can't build it up manually is because we don't know the format. It's different for every graphics card. We don't know what the push buffer, command buffer stuff has to look like, right? We have no idea. These are often called command buffers, by the way, not just push buffers. We don't know the format. So we got to call in OpenGL, or again, Direct3D, or Mantle, or anything else. We have to call into that to construct these things. Once we have constructed them, then we, at some point, trust that the driver will take a ring transition, kick it off, and the GPU will start doing it, right? And that's what happens. So it's a very, very buffer-driven. It looks a lot like our renderer looks right now. You build up buffers, then you say, hey, go render this, and it does. The only difference is, instead of it rendering right then on the CPU, it gets handed off over the PCI bus, over the graphics card, where the graphics card will do it while we're doing other things. We don't wait, we just kick it off, it goes and does it, and later we get the results, right? So that, in a nutshell, is what we're going to be doing. And so when we call our OpenGL calls, they're somewhat high level, right? Because they're card agnostic, so they just kind of have some basic ideas of the things that graphics cards need to do. And then the driver will take care of translating those somewhat high-level things into whatever the actual push buffer stuff was you needed to do. Now, if this were a locked machine, meaning we knew the exact hardware configuration of it, and we had all the docs and everything, you could imagine doing the low-level version of this code, like on a Raspberry Pi or something, where you know the format of the push buffer, you know how to do a ring 0 kickoff of the thing or whatever, you know all that, you could write all this yourself. There's no magic to it. It's not like we couldn't write it ourselves. The problem is on a PC, there's no way to write it yourself. You have to run across multiple graphics cards. You have to run on graphics cards that are completely undocumented and that you don't know the push buffer format for. So yeah, good luck. You got a GeForce Titan in there. You'll never be able to talk to it with your own code because they won't tell you how it works, right? So basically what we're doing is we're calling through OpenGL to do those operations that we know we could conceptually think of how to do if we only knew what the graphics card actually did, and we could abstract across multiple ones, right? But that's what's going on. So the thing that we will try to do tomorrow probably, because I'm going to go to questions here. The thing that we'll try to do tomorrow, and maybe we'll even have an HDMI capture card if I'm lucky, the thing we'll try to do tomorrow is we will try to do the very simple operation that is as follows. We have our main memory. And we have our screen display. We made this with our own renderer, right? What we need to do, here's the GPU mem. Actually, I threw that a little further away. Right? What we need to do is we need to take this and we need to put it into the GPU memory. So that has to happen. And by the way, this is a bit of a lie. The reason this is a lie is that GPUs oftentimes don't store things as continuous linear bitmaps like we do. They also store them with a thing called swizzling that's designed to optimize the memory access. You don't have to worry about that right now, but just so you know, this is a bit of a lie. This might actually look more like this totally discombobulated version of that guy. So we need to move our image over, right? So that's step one. Move over. I should say, let's just say step one, transfer our bitmap. Step 2, we have to then tell it that we would like to draw that bitmap to the screen, right? So step 2 is we need to take the screen and fill it with probably what will end up being like 2 triangles, right? Because GPUs are optimized for drawing triangles. So we draw like 2 triangles that encompass the whole screen, okay? So we need to draw 2 triangles, and those 2 triangles have to map to our bitmap. So we need to use textures, right, to grab this part of this triangle and put it here, and this part and put it there, right? That's all we need to do. And we just need to do that with a direct copy, right? We don't want no Z buffering, we don't want no shading, we don't want no nothing. We just want it to be directly written to the screen. And then 3, we have to display it. And we've already got that, right, because you saw us clear the screen and we did the display. So this is all we have to do. It'll take us a little bit of doing to do it because it's a little bit cumbersome to do these things. Because again, once you start talking about going through APIs and there's 2 separate sets of memory and all these other sorts of things, things get a lot more complicated than when they're just on the CPU. It's one of the reasons that I really just don't like the idea of GPUs. I wish that we just had super beefy CPUs. The world would be such a nice, better place. Be a lot more reliable too, but we haven't ever gotten there. Someday I hope we do. I'm going to go ahead and go to the Q&A. So if you have questions about how graphics cards work or what's going on there, ones that aren't too hardware specific so that I can answer them, because I'm not a hardware guy, so I can't really tell you some of the real nitty-gritty stuff. But if you have those questions, please go ahead and send them now with a Q colon in front of them, and I will try to give them an answer. Ratchet Freak, you can, instead of 2 triangles, use a single triangle twice as big. It avoids the overdraw at the diagonal. Sure, yeah, you can do lots of things. You also can just not do a triangle draw at all, right? Because sometimes they actually have the concept of a blit. So if you're worried about the actual speed, there's a lot of different things you can do. But I would try to very strenuously point out the fact that you really should not be thinking about that in any way at this point, right? Like literally, I have no idea why that would even be entering your head at this point, because you have no idea if this would even be slow. In fact, I can guarantee you that it won't be slow. The diagonal is so few pixels that it's literally completely irrelevant, right? Most of the time, you don't do that operation for speed, the like giant triangle thing, this thing. Most of the time, you don't do that operation for speed anyway. The reason you actually do it is to avoid, if it's something that needs to do like a operation that at those points, if you operated on them twice, you would get an incorrect result, right? But the speed difference between those two is like really just not very, very not important. Quick CPU question. All it does on bare bones physics level is run electrons through if statements, right? Go left, go right, etc. with transistors. So I think I would say, although I'm not the right one to ask because I'm not a hardware guy, I think I would say more like it's either go forward or stop. Because I believe a transistor usually is like something like this, right? Where there's electrons going this way, and there's a thing that will either stop them from going or let them go. So I don't think they do left or right. They either go or don't go. So I don't know. But maybe you're right. Maybe it's left or right. Maybe it's forward or into the sink, right? So they do go in 2 different directions in that sense, I guess. But I don't know. I'm not a hardware guy. I know nothing about hardware. Can't you run a Xeon Phi as your main processor, or did they make them dedicated only? Not like price performance makes sense there. You can run a Xeon Phi as your main processor with the second one, I believe. But you can't quite. So The problem with that is they nuked the texture units on it. Otherwise, that pretty much would be exactly what you would want, right? But it used to have texture units, and now it doesn't. And I don't know if you can really do high-performance graphics without texture units. I'm not sure. Chronal Dragon, what barriers are there currently from just using the CPU as a GPU? There aren't any. It's just cost, right? So if Intel wanted to, like the person who just mentioned the Xeon Phi, the Xeon Phi is like faster than a GPU at a lot of stuff, big computation stuff. So there's a few things that GPUs do better based on how the like I said, texture fetching and stuff like that. But it's just cost. It's like Intel doesn't want to sell $2,000 CPUs to everyone because they know no one would buy them because they can't afford them, right? And so, at the moment, it's mostly about cost where, I shouldn't say cost, I should say margin maybe. Like, Intel wants to be able to sell chips for $100 or whatever, and make $70 off it or whatever. I don't know what it is. They want a fairly fat margin there, right? They don't want to do something that's like $700 that they make where they have to pay $650 of that is cost or whatever, right? So like Nvidia and those people, like their margins are, I think, much lower than the margins that Intel has for CPUs, and so it's really just a cost thing. I think Intel could make, they could make something that was really fast and was just a single one that did it, but Ace Flameseer, can we make a first-person 3D mode of the game just for education? No. Cubic Lab, where does the PS4 X-Bone processor lie on the CPU-GPU spectrum? It's basically like the thing. It's like a lot like Skylake. So where did I draw that guy? I don't know where I drew him. I'll just draw him again. So basically, like if you've got like a Skylake chip, it's something like it's something like this. I mean, I don't know if it's actually that way. I think it's 70%, not quite 75, so this might not be quite right. But it's like that. And it's just one chip, and then you've got your memory, right? And the same thing is true basically for the AMD like Bulldozer line of stuff, right? Which like the X-Bone and the PS4 are basically like, we can't know exactly what they are because they don't let that out of NDA, but they're basically like an AMD Bulldozer kind of a type of thing. So it's basically the exact same thing, right? It's like, oh, there's some CPUs and then there's a big old GPU on a die and it looks like that or whatever, right? And not much is really different. It's exactly the same. You can, because the big difference really is that because that they're both on one chip, you can short circuit things to the GPU really quickly. So you can, kick off computations to the GPU really quickly when it's on the same die like that. And so that you don't have to worry about that PCI bus transfer nonsense. And they all got shared memory, so it all just kind of parties out of here. It's a better architecture, right? Like this would be, the best possible thing would be like if Intel and Nvidia got together and just welded them together, or if Intel just decided to like make some $1,000 chip that had like a 40 cores, 40 I don't know, not 40, I suppose, more like 256 ALUs or something on it or whatever. That I don't know. That would be the best possible thing for sure. Quartertron says, Intel has killed off many projects that made good money but had bad margins. Yeah, exactly. I mean, one of the things you have to remember is that it's a little bit of a problem where, when Intel comes out with a GPU and it's not very good or something, right? The temptation might be to think that like, oh, they just don't know how to make a GPU as good as Nvidia or something, right? But the reality is that that's just not the case. It's usually more like they had a very specific price target and margin target they were looking for, and this was the chip that fit in that target. because Intel's fab technology like annihilates Nvidia's fab technology, to say the least. So, you know, if they wanted to, they could fab a pretty amazing GPU, I'm quite certain. But that's just not where they're going to make their money. And so, you know, if there was a market for $2,500 GPUs in enough quantity, I think suddenly you'd see it Intel 1, right? And the other problem is software. Intel can't write drivers to save their life, right? Can't do it. No idea how to make software. Intel's never known how to make software, probably never will. They're getting better than they used to be, but they're really bad. And so a lot of the finesse in getting games to run well is also at having a well-functioning driver, because they're very complicated. They do a lot of behind-the-back optimization and a lot of, like, you know, complex stuff. Intel has traditionally had a lot of trouble with that, and so that's another big stumbling block, right? That has nothing to do with being able to make a fast piece of hardware. So. Long Billion, I've been told that lots of graphics drivers optimize for specific games at the driver level. How does this fit into the equation? How do those optimizations make some games run better? So what happens with that is exactly what you would expect. This process that I just talked about, right? It's over on the side here somewhere, right? So this process where we're building up the push buffer, what happens is the driver writers will look and they'll say, oh, okay, you know, we have our driver fully instrumented. So if we want to, we can go and we can run, you know, Battlefield, or we can run Grand Theft Auto, and we can look and see how it's building up the push buffers, like what kind of calls it's making, and what it's doing. And since we know how our chip works best, we can look for ways in which they could have done what they did more efficiently, and we can make that happen, right? We can. It's sort of. It's a lot like a fuzzy match kind of a thing, right? It's like, oh, I know that, like, in GTA it does like this command, this command, this command, this command, this command, or whatever, right? And I know that if I just did this earlier and switched the order of these two, it would render much faster, right? So the driver just does that behind your back before actually kicking the stuff off the GPU. Similarly, they can tune all sorts of stuff about, like, how often they kick things off, how big the kickoffs are, what they wait for, where the sync points are. There's, like, all these things, like, with that sort of process of managing where the GPU is and what memory goes where when. All of that, obviously, right, you can imagine is very complicated. There's tons of asynchronous stuff there. They can tune all of that to the game and make it run better, right? And so that's why they do a lot of detection to see when people are doing specific stuff, and they do that based on the game oftentimes. They're like, oh, I know this game, when it does this thing, it's safe for me to perform this operation, so I do. SSS McGrath, why does everyone good that works at Intel hate Intel, yet simultaneously Intel's engineering is so far ahead of everyone else's, it doesn't compute? Well, I mean, if you want to make chips, you need that kind of a fab investment, and there's not very many places that have it. So if you're a very smart hardware designer, where are you going to go? So you may hate the bureaucracy or whatever else, but at the end of the day, if you're going to do a lot of chip design stuff, I think that's where you end up, right? Gary Johansson, what did you think about Larrabee? I love it. I love it, love it. I wish that Intel hadn't essentially killed it with bad software practices. I mean, that's the long and short of it. I wish they had I wish that's what I was programming on right now. I wish the Xeon Phi still had texture units. Does Vulkan fix the problem with OpenGL of not being able to transfer buffer objects between processes with separate address spaces? Transfer buffer objects between processes? Why are you trying to do that? Are you talking about like a Chrome style security system? Why are you trying to transfer buffer objects between two processes? And no, I would not be allowed to say either way, but I'm curious why you want to do that. Not that I think it's bad for it to support that necessarily. I'm curious. Angus Holder, Intel's compiler is meant to be really good, right? Yeah, so apparently like one guy wrote the IPC thing or whatever, the auto-parallelizing one, that's supposed to be pretty good. And it's like some guy wrote it who was really good or something like that, right? Their normal compiler stuff in the past was not that good. Let's see. Can you give us some insight without breaking any NDAs how different from OpenGL console graphics APIs are? Well, yeah, I mean, so I think the right way to think of it is more that none of this stuff really matters at all. It's more about just whether or not you can count on certain things. So the big difference between programming on a console and programming on a PC in terms of how you deal with the graphics card is not that OpenGL is somehow so much different. The concepts are all basically the same. The stuff is all the same. Sometimes you can even run the exact same shaders, right? The big difference is that you can count on stuff. Like, I know that this chip takes this long to do this thing. I know that this memory is shared between the CPU and the GPU. I know that the CPU can directly call the GPU to do some operation, right? And so you can bring those things into the code and use them. And those are very different from what you could do on the PC, because on the PC, you could never write that code. It wouldn't run abstractly on all the different PCs out there. So that price you pay for having a heterogeneous computing environment is simply that you cannot do those things you can't do on a console. But nowadays, that difference is very small sometimes, because a lot of times now, Sony doesn't want to tell you how the thing works, or Sony wants to reserve one core for their operating system. So now you can't even count on using all of the cores of the thing, right? It starts to look, as these things become more like living room PCs and less like quote-unquote consoles, it's a lot more like the PC every day. And so the degree to which you're doing Mr. Fancy Pants stuff, when you look at like the PlayStation 2, for example, versus PlayStation 4, night and day. The PlayStation 2 is like crazy town. And the PS4 is like, it's basically like programming a PC with some extra stuff you can do because you know. Chrono-kun, sharing objects between applications without CPU overhead. Yeah, you got to tell me why you want to do that. I don't know what the use case is. Explain to me why two applications want to share an OpenGL object. Again, not saying you shouldn't be able to do it. I'm just curious. Canuckles, why do you think there's no games about programming hardware history of PC hardware? The domain is unimaginably rich. I don't know. I mean, TIS 100, I guess, was sort of like that. People seem to think that was sort of interesting. On the other hand, it's not like a huge seller. So it's probably like because the market's not that big. Might be one of the reasons, right? How does GDDR RAM for GPU, or concept of memory chip design specifically for GPU, enter into this picture? Well, it's actually relatively important. So again, I'm not a hardware designer, so I'm not going to try and tell you specifically why it's important, because I'd probably just be wrong, right? But let me give you the gist. Let me give you the gist of it. So let's take the instruction set designed by Intel for SIMD. And I'm going to show you something we already did in Handmade Hero, right? In Handmade Hero, we did a thing where we computed 4 addresses for textures, because we wanted to do bilinear filtering, right? I'm sorry, because we were operating 4 wide, I should say, right? So we had 4 pixels. Now, each of those pixels wanted to look up, right, into some piece of memory and grab what was there. But even though we computed it 4 wide, we then had to downshift by extracting each one individually, executing a scalar, like a this is SIMD 4 wide, scalar operation to go fetch the thing, then stick it back up into the SIMD, and we had to do that 4 times, right? That's a classic example of how the architecture of the memory system is not supporting the architecture of the computation. What we want to do is have 4 addresses and then issue one operation that's like, go fetch them all, and it gets them all, right? And so what should have happened And you can see this here. See these fetches? See this nonsense right here? Look at this, right? Here's all this code that's doing 4 pixels at a time. All of a sudden, we have to do it manually, right? Do you see how we have to blow it out to everything is now manually done 4 times, 4 times, 4 times, 4 times. Always 4 times, right? And that's a classic example of the memory subsystem not supporting the ALUs. And so I imagine, and I don't know, but I would bet your bottom dollar on the GPU, you don't see anything like that. I bet you've got a 16 wide fetch that does full scatter gather. So it just takes 16 addresses, it goes out and gets all 16 and brings them back. Furthermore, I bet that's a texture unit so that those can actually do the bilinear sampling in the memory. So I bet the memory never even has to transfer that stuff. It probably can grab up a bilinear sample in like one go or something, right? And again, that's all because that memory is designed for that. I just think that's what should happen with memory. Like, we should just have that with memory on the CPU too. I would like to see it go that way. Because like I said, I just want CPUs. I don't want GPUs in the future. I just want a big old beefy CPU, but you know, I'm probably not going to get it. Could you one day maybe do a pre-after stream short summary about your thoughts on OS design and what you would do differently given current hardware? That'd be something I'd probably talk about in a more formal setting at some point. But it's not going to be anytime soon, probably in about a year or so. I mustered up one more. How come the Witness has 4 GB of RAM as a minimum requirement? I don't doubt it has great optimizations, as John is an Apex level programmer. Is it because nowadays everyone has 4 gigs at least and they thought it's unfeasible or too limiting to go below that? What can be the design behind that requirement? So I feel like it's probably not really my place to answer that, but the answer in sort of the abstract sense is that actually the Witness's memory, the way that their architecture works in the Witness is actually not great for memory. So it does not have great optimizations for memory at all. It's not particularly good at that. And I can tell you the reason why that is, and the reason is because when they started the Witness, John was thinking that it was going to be a game that would be like 5,000 entities or 6,000 entities to make up the island or whatever. The actual count is like 65,000. I think, entities. And so the game grew from a code base and never was really redesigned. It grew from a code base where it just can't really handle paging very well. It has sort of asset streaming shoehorned in not a particularly good way. And the actual footprint of the game itself, it's not really designed to use small amounts of memory. That said, does it actually require 4 gigs to run? I don't know. I'm not really sure it does. I think they probably picked a fairly high number just because why not? Like any machine that's probably fast enough to run it probably has 4 gigs of RAM or something, because it's a pretty graphics intensive game, right? So I don't know. But yeah, the reason that if it does actually take 4 gigabytes of RAM, and I don't know if it actually does, but the reason is very simply because it's not designed to be memory optimal at all. It was never even a goal of the development process to keep that number low, I guess is what I would say. So like literally, I don't want to say literally, but almost no engineering effort was ever expended by anybody to make sure that happened. Elvin, why does it always seem like PC games claim that they require much more hardware power than they need? Do they want the extra power just in case something goes wrong, or what? Well, a lot of the reason is to cut down on support, right? You don't want to necessarily come out and say, this is the absolute bare minimum that my game could run in. Because then like some user like is running like 12 things in the background and has like their World of Warcraft game open, like doing something, and then you try to run the game and then they complain to you that it doesn't work on the minimum system spec or whatever, right? And so part of it is just like, you don't want to set your minimum system spec down to like the most razor thing. So if the witness can actually run in 3 gigabytes of memory, they might not have an incentive to say that. They might be like 4 gig, you know, make sure, you know, let's not push it, right? And so I think most games probably follow that. Better to be safe than sorry a little bit. You want some margin for error because it does lead to more support hassle when people, because once you say this is the minimum spec, people are going to expect it to run on that spec, and you're going to get people complaining if it doesn't. So you want to make sure you don't cut it too close to the wire, right? Question, having OS level support for GPU resources for compute and graphics so that 3D graphics tools can interoperate efficiently, e.g. in VFX production where you have lots of tools using the same data. I see. So you're basically talking about, you know, and this is probably not quite right, but like I've got Mudbox and I've got Maya, and I want them to just share the same vertex buffer so they don't have to transfer it back and forth. That's totally reasonable. I have to say I don't actually know if Vulkan does that or not, but I wouldn't be able to say even if I did, I don't think. But I honestly can say I don't remember. It was not a usage case I ever looked at. Long Boolean, what would be a disadvantage of having a big beefy CPU, or are there none? Well, I mean, the disadvantage is the price. Have you seen that guy that is going to recreate Quake in Handmade Hero style? I haven't actually watched the stream, but some Handmade Hero people did tell me about it, which sounds cool. I think that's a really good idea. Punka, how long do you expect this project to take? I think I've ballparked fairly consistently that it'd be something like 600 episodes. And right now we're on episode 236. So 2 more years? I don't know. At an hour a night, it's pretty slow, right? And a lot of stuff is like this where you don't even get any work in a day because you're explaining things. From what I get, Fallout 4 just allocates itself an 8 gigabyte block. That seems fine to me. I mean, if they actually need it, if they're actually doing something with that. I mean, you know. Quick question about strict aliasing due to your forum post, not defending it, but how would you propose compilers to understand that pointers do not overlap to optimize loads and so on? Not sure how we could improve generated code without having that kind of guarantees, assuming we need to still support old code. I don't want compilers to do that. I don't want compilers to do that. When was the last time in Handmade Hero, which by the way is doing software rasterization, where we were like, oh no, we have to start compiling this in optimized mode at all? Nowhere. It's only the pixel fill, right? We're not even compiling with optimizations on. The game ran at 60 frames a second. The pixel fill is the only thing, right? So if you just write relatively sane code, you don't need the compiler to be doing these things for you. And so all I really want is the ability to tell the compiler when I care, these two things don't alias. That's all I need. And that's in there, restrict. I can tell it that the 2 pointers don't conflict, right? So it's bad programmers writing bad code and then compiler writers deciding to try and optimize that code for benchmarks or whatever, right? And like that is not how it should go. That is really bad. And you end up costing good programmers, the people who don't care about these things, a lot of time because you introduce bugs in their code because you choose some strict random thing in the spec that no one should ever care about and that shouldn't have been in there as a way of rationalizing some stupid optimization that's there for somebody who like instantiated 30,000 levels of templates and was like bummed that their code didn't run fast. It's awful. Awful, awful, awful. I hate that stuff. It's bad programmers costing good programmers time, and I hate it. Andrim2, out of curiosity, back then when it came out, was GDI just a wrapper for OpenGL? Do you mean the other way around? When it came out, GDI was GDI. There was no such thing as OpenGL. GDI was Windows' graphics interface. When OpenGL first got introduced into the Windows ecosystem, which I believe was NT351, what it was a rendering library that sat on top of GDI, and it was a software renderer. So it rendered in software and output to GDI. So it was literally just a software renderer that sat on top of it. Later, as hardware became available, it started being able to accelerate it. And at the time, there was one Silicon Graphics card I think you could get to plug into very expensive, to plug into a PC that did some kind of acceleration. I remember those being around back in '92 or something, but I never actually used one. I saw them sitting on the shelves at Microsoft. Caleb, restrict doesn't seem to work with VS 2013-2015. I don't really know much about that. Like, I haven't spent too much time with it in 2013-2015. It used to work. NORAD, isn't restrict like stupid limited though? And you don't have alias, one that's definitive at least. No, restrict isn't. I've never really had a problem with restrict. I mean, yeah, it'd be nice if there's a better one that said like these two pointers don't ever collide, whereas this one might with this other one or something. But I've never really found that to be a problem. Why is it that games get more difficult to play as Windows OS gets more advanced? Well, it's because the people who design the platforms are getting worse, honestly. If you're talking about why they're less likely to run. Originally, it was just DLLs. That was the only thing that could be broken. Then you started getting into the side-by-side assemblies, manifests, registry. All that stuff was just really bad ideas. Bad design on the Windows architecture. And so now it's almost a given that if you take a game executable, it won't run. There's no question that if you take a modern game executable and try to run it, it won't run. You have to install a bunch of prerequisites first, right? I think that's about it. We are out of time. So I am going to wind down. Save this off. So I will hope that I can find some kind of a DV DisplayPort to HDMI converter, or I guess a DVI-X to DisplayPort converter. Either one would be fine, actually. Maybe it will. Maybe we'll find one. Maybe I won't. So hopefully tomorrow we'll have a way. I'll do the coding either way, but hopefully I'll have a way for you can actually see that the results work, so that I'm not the only one that see whether they work. At some point, either way, I will get the converter working so that at least by next week we'll be able to be doing OpenGL that can stream properly. Either way. So anyway, thank you everyone for joining me for this edition of Handmade Hero. It's been a pleasure coding with you as always. If you want to follow along at home, you can always pre-order the game on handmadehero.org, and it comes with the source code so you can follow along. We also have a forum site you can go to ask questions, a Patreon page you can use to support the video series, and a tweet bot which tweets the schedule at you. So if you want to know when we're going to be live, that's the place to check. But I will tell you right now, it's tomorrow at 5 p.m. Pacific Standard Time, unless I post otherwise on the tweet bot. So that's it for today. Until tomorrow, have fun coding, everyone, and I'll see you guys on the internet.